Alright, section 12.5 is about volumes of pyramids and cones. Our objectives are to find and use volumes of pyramids and cones, and our central question is how can you find the volume of a pyramid or a cone? So let's start with the pyramid. To find the volume of a pyramid, we have a formula. We take 1/3 times the area of the base times the height of the pyramid. And this formula works for our right pyramids and our oblique pyramids. Just a refresher, a right pyramid is from the apex perpendicular to the base. When the height is perpendicular to the base, that's a right pyramid. When the apex is not perpendicular to the base, that is an oblique pyramid. Alright, so let's use this new formula to find the volume of the following pyramid. So let's start by writing out our formula. Alright, so we know it's capital V equals 1/3 times area of base times height of the pyramid. So that capital B standing for the area of the base means we need to figure out the area of the base. Since our base is in the shape of a triangle, that means we need to use the area of a triangle formula, so 1/2 times little b times little h. So this applies to just the triangle's base and height. We know the base length is 4 and the height is 6. So 1/2 of 4 times 6 is the result of 12 meters squared. So capital B, area of the base, equals 12 meters squared. So we're going to use that value in our volume of triangle pyramid. Since we know the height of the pyramid is 9 meters, we can plug in the 12 and the 9 and take 1/3, resulting in 36 cubic meters. Alright, our next core concept is the volume of a cone. So we find the volume of the cone using the exact same formula. 1/3 times area of the base times the height of the cone. And this works for a right cone and an oblique cone. Area of the base this time will always be pi r squared. Whereas in the pyramid, our formula for area of base will change depending on the shape of the base, but for cones, it's always the base is a circle. Alright, so let's use this new formula to find the volume of the following cone. Let's start with the formula. So you know it's 1/3 big B little h equals, in other words, 1/3 pi r squared times h. So we know the radius is 2.2 centimeters, and we know that the height of the cone is 4.5 centimeters. So for the capital B value, we can plug in the 2.2 in for r and square that, and that gets us 4.84, and then leave it in terms of pi to keep it exact. So 4.84 pi centimeters squared is the area of the base. So we can plug in both those values. For capital B, we would plug in the 4.84 pi, and then for the height, 4.5. So that all multiplies out to be 7.26 pi feet cubed, if you want to keep it exact, which I want you practicing exact, and then type this in the calculator to get approximate, round to the third place value, the thousandth place. So 22.808 cubic centimeters. Alright, let's find Khafre's pyramid, which had a height of about 144 meters and a volume of about 2,218,800 cubic meters. We want to find the side length of the square base. So let's start with our formula. We know volume of a square pyramid, or any pyramid, would be 1/3 times the area of the base times the height. And we know that the shape of the base is a square. And to get a square's area, we take the side times itself, so side squared, s squared. And the side length is unknown, so we're going to call it x. So when we plug in x to our formula, we know that the area of our base is going to be x squared. So we're going to plug that in for capital B. And then the height we know to be 144 meters. And then the volume we happen to already know to be 2,218,800 cubic meters. So we'll substitute that in for capital V. So we multiply the 1/3 times 144 and then divide on both sides. So we get x squared equals 46,225. Square root both sides, resulting in the positive and negative value of 215. We know we can eliminate the negative value because you cannot have a negative length. So originally, the side length of the square base was about 215 meters. Alright, so next we want to describe how multiplying all the linear dimensions by 1/3 affects the volume of the rectangular pyramid provided here. So of course, let's look at our before change values. We know that the length is 9 meters. The width of our base is 6 meters, and the height of the pyramid is 18 meters. So let's figure out our volume based on the before changes. So we know 1/3 times area of base is 9 times 6, and then our height is 18. So multiply all that together to get 324 cubic meters. After the change, let's take a look at our new numbers. So now the length of the base will be 3 meters, because 1/3 of 9 is 3. And then the width is 2, 1/3 of 6 is 2, and then the height now is 6, 1/3 of 18 is 6. So now let's plug in our numbers into a formula. So 1/3 times the area of the base, so 1/3 times 3 times 2 times 6, and that works out to be 12 cubic meters. So how did the new changes affect the volume? Well, multiplying all the linear dimensions by 1/3 results in a volume that is 12 divided by 324. Always divide the new by the original, and you can compare 1/27 scale factor. If we rewrite that in terms of the original scale factor, 1/3, that's 1/3 squared. No, sorry, that should be cubed. 1/3 cubed times the original volume. Alright, so I just fixed that on our screen, so it should be 1/3 cubed. 1/27 becomes 1/3 cubed. Alright, one more example. We're changing the dimension in a solid. Let's see what the effect of doubling the radius has on the volume of the cylinder. What effect? Alright, so we look at our before, and before we make any changes, the radius is 3 feet and the height of the cone is 5 feet. We already know and are familiar with our formula for cone. So 1/3 pi r squared times the height, so pi times 3 squared times 5, so 3 squared is 9, and 9 times 5 is 45, then 1/3 of 45 is 15. We'll keep it exact and compare it to after the change. So after the change, we get a radius still of 3 feet. That didn't change, only the height, only one dimension changed, and it changed to 10. We doubled the original, which is 5, to get the new, which is 10. Plug it into our formula, so 1/3 pi r squared, so 1/3 pi times the radius, 3, squared, times the height, new height, 10. And then 1/3 of that is 30 pi. So how does this compare? Let's see. So doubling the height results in a volume that is 30 pi divided by 15 pi. Remember, divide the new by the original to see what the effect is. It looks like it's 2 times the original volume. Alright, and then our last example is finding the volume of a composite. Looks like our composite is made up of a pyramid and a cube. So that means we need to, in order to get the volume of the whole solid, we need to add the volume of the cube to the volume of the pyramid. Alright, so let's get our formulas for both the cube and the pyramid in place. So to get the volume of the entire composite, we need s cubed, so all of the dimensions of the cube multiplied 3 times. It's the same dimension. And for the pyramid, 1/3 times the area of the base times the height. Now to get the parts of our pyramid, let's start with that. So the height is 6 meters, and the base side length is 6. And we know that all the side lengths are 6 because it's a square pyramid. So to get the area of that base, it'll be 6 squared. And then to get the height, we have 6. And then the parts of the cube is all the sides are 6 meters. Alright, so let's plug into our master formula here. So we have 6 cubed plus 1/3 6 squared times 6. And that all multiplies out to be 216 plus 72, combined to be 288 cubic meters. So the volume of our composite solid is about 288 cubic meters. And that's all for the volume of cones and pyramids. See you in class.